Yeah, I'll be talking about medium range thermosphere, ionosphere storm forecasts and a newer thing we've been working on called the Space Weather Forecast Testbed, which we're currently talking to CCMC about to deliver to them. And this was one of the projects in the NASA NSF Partnership for Collaborative Space Weather Modeling. And these are my collaborators here at JPL, University of Southern California, U Maryland, and U Michigan. And this team here is all sort of, one person from each place. Well, we're a couple of us, and one person from each place are actually co-Is, and then Michigan is participating through Spiro Antiochus and Tomasz Gambozi. So maybe some of you know this idea. It's the idea of a medium range forecast, the terminology borrowed from the weather folks, medium range forecast being 1 to 3 days. And that's sort of very convenient in our case because if you detect a coronal mass ejection at the sun, at the solar surface, you have about 1 to 4 days typically before it hits the Earth, and you can contemplate the idea of forecasting in advance what will happen at Earth. And a lot of people have said this is just way too challenging, we can't do it. And my philosophy is we've got to start thinking about it, start moving in that direction so we eventually can get something going. If we wait for the solar forecast to be perfect, we'll be way behind in this area. And I also believe, and I said this in my CDAR science talk last June, I believe that a forecasting focus is very good for our community. I don't really talk about that in this talk. I didn't want to repeat that material, but I urge you to go to the CDAR online CDAR science highlight and look at why I say that. And I'd love to hear your feedback on that. So I give a little bit of context, and then I really spent a lot of time thinking about what we should forecast, because if we just naively think of a forecast in the terms that the weather folks have done it, I think it's going to be way too complicated. We're not going to be successful. So we spent a lot of time thinking about what do we want to forecast. That also ties in some ways to the science. I show a case study of an interesting high-speed stream event, which really had us scratching our heads. We've talked to Wenbin Wang about it and others, and we're currently writing it up. Then I'll talk about the test bed that I hope people are interested in using to sort of get themselves involved in a forecasting orientation for our field. So the basic idea, and actually Stan gave a talk on this some time ago, the idea that we actually have a chain of these models. We could literally run a first principles model from the sun through the heliosphere, down through the magnetosphere to Earth. And I think really, as people interested in modeling, as modelers, that should be part of our toolbox, part of our interests is forecasting. I think that's just a natural extension of what you do in modeling. So this suite of models exists, and our focus, of course, is the thermosphere, ionosphere, but driven by the solar wind. I'm going to backtrack a little and go to a paper by George Sisko and Stan Solomon, where they really looked at this problem, the data assimilation problem, in detail, and they came up with a very nice graph about availability of data and sensitivity to boundary conditions in different domains where you might apply data assimilation. Now, data assimilation was invented to do forecasting. The whole purpose of data assimilation, which is sometimes forgotten, is to initialize a physics-based model, then run that model forward in time, and that's your forecast. And so what we de-emphasize data assimilation in our effort, not for any great reason, but if you're doing a multi-day forecast, in some sense, your data assimilation is the surface of the sun. And then you're trying to forecast what the heliosphere, what the solar wind conditions are going to be, and then you map that into the ionosphere thermosphere. But you can see on this graph, if you're in the troposphere, the lower atmosphere, you have a lot of data, and the system is basically persistent. It will remember where it's been for a few days, and there's not much to interrupt that. Obviously, you can have extreme weather situations, but globally, it has a very high memory. In space weather, the memory of the system is much lower, and ionosphere thermosphere is somewhere in here. It's got less data than the troposphere, and it's much more sensitive to boundary conditions, particularly if you're thinking of the case where it's going to be hit by a solar event. The memory is pretty much wiped out. I mean, that's an oversimplification, but a lot of what you had been forecasting will get reset when the solar wind hits the system. And so we de-emphasized the traditional data assimilation aspect, although I'm very supportive of those efforts, and eventually those efforts will be folded in, but we didn't focus on that.
But Tony, I got a comment. I'm so pleased that one of axis was was how much memory the system had, and the other axis was basically how much a system is driven by its internal dynamic as opposed to externally opposed things. And George collapsed it all down into one line.
Right, right. So this is more than sensitivity to boundary conditions, is kind of what you're saying, maybe.
Yeah,
or there's a combination of.
There's this business of how much memory.
Right, right.
The ocean has a lot.
Right.
The magnetosphere only a little.
Right, right.
But then there's this other aspect, which also kind of ties into this question of how chaotic things are, which is the extent to which something has an internal dynamic.
Yeah.
By its own internal processes, let's say that.
Mm-hmm.
And the extent to which it's driven by something that happens outside of it. And part of the point of that, part of the whole point of this was responding to people who wanted to see magnetosphere data assimilation.
Right.
And part of the point was, well, that's hard.
Yeah.
Because the magnetosphere doesn't have much memory, and it's bossed around by the solar wind.
Right. Right.
So,
right.
What are you going to do with data assimilation?
Right. Well, I think you're saying that there's different roles for data. Yeah, it's a totally different thing. So, yeah. Oh, completely different. Right. Yeah, I agree with that. Yeah. I mean, yeah, I completely agree with that. So, the next question then is what is an ionosphere? What is a thermosphere ionosphere forecast? Well, okay, so. If you think traditionally, a forecast is the output of a first principles model stepped forward in time. And again, you use data assimilation traditionally to initialize the model, and so it's an accurate forward model. In this case, we would drive the model with a solar wind forecast. And there's a lot of information we simply would not have in that case, but if we could get an accurate solar wind forecast, that is essentially what's going to drive the storm behavior of the model. The model produces tons of output, and my concern was if we just try to take averages or RMSs or whatever, it's not going to give us a lot of insight into what's going on. So we decided to simplify what we get from the model, just 2D total electron content. That's what we originally focused on. There's so much more you could look at. The good thing about TC is there's lots of validation data. And so what that means is you can always compare a forecast, or what we obviously have been doing is simulated forecast or hindcast, if I'm using that term correctly. Just, we're not actually doing a forecast, but we're pushing the system as if we had no information except the solar wind coming in, driving everything with the solar wind, and seeing what the output of the model is. So you can do that with an actual measured solar wind, in which case you assume your solar wind forecast is perfect, or you can actually do it with a solar wind model, and those are different cases. But so what is a thermosphere ionosphere forecast? And part of what motivated our thinking on that is sort of the many decades of research into storms, starting way back, well before this. I mean, Klobuchar and Mandela were doing this work in the 70s, but they synthesized it again in 2006. And one way to think about a storm is sort of in this picture. There's a latitude range. This is really North American centric, which is fine. This is one region. There's a latitude range on this axis, and there's time on this axis. And so this is an average of 70 to 100 storms. Okay, so these folks have been doing this for a long time. And basically, the storm goes through phases. It goes through a positive phase, and that's what this is. This is change of TC. So notice they're not predicting the actual weather conditions. They're predicting the change in the weather, which is not what we do here on Earth, but that's what you do in space weather. You predict the change. So you see an increase in TC over some period, let's say it's about a day, and then you descend into what's called the negative phase, where you see decreases in TC, and that persists for several days. So that's the classic storm picture. So we felt that the way to move this forward is not to actually predict what's the TC over a given location at a given time, but is there a positive phase? How long does it last? Is there a negative phase? How long does it last? What latitude bands does it cover? And there's other effects here like auroral enhancements and trough depressions and so on at higher latitudes. But that's the basic idea. rather than, so this is an average picture of a storm, and in fact this could be considered a forecast, right? You could say on average this is what a storm looks like.
So
Yeah.
can you expand on why delta TEC is more important than absolute TEC? I mean, maybe it's just because the data is available and so you can go after delta.
I would say the reason is traditionally would be because TEC itself is so highly variable. If you look at it, say, on a monthly time scale, within that month, it's going to vary 20, 30%. It's going to vary by magnitudes of this magnitude. So if you say, what's the TEC, you're kind of fighting two things. You're fighting its natural variability, how it varies day to day over a month, let's say, and you're fighting what the storm did. So by isolating what the storm did, you're maybe closer to understanding. Now, what people have begun to look at recently is the preconditioning, the fact that if the TC happened to be low that day, how it behaves during a storm is going to be different. And there's also seasonal effects. There's seasonal storm time effects. Different seasons, the storm will behave differently. So, but that's the sort of why. It's just the natural variability is pretty big.
Day to night solar cycle.
Yeah, day to night. In fact, you should see, yeah, that's a very good point about day to night. This is, do I not mention here? This is local time, actually. Since it's in one geographic sector, this is actually local time. And local time dependence is very important. I guess I didn't highlight that. Okay. So again, I could just say, well, let's make a forecast when that CME hits. This is what's basically going to happen, and I think that's pretty much true. But we don't get any sense of the variability. And for example, it could be a high-speed stream or CME-driven storm, different magnitudes. There's no storm strength in this. This is an average over many storm strengths. But this was sort of an important advance in our knowledge to at least characterize an average behavior. I think that this average behavior is probably pretty well modeled these days, and people feel like the models reproduce it pretty well. And I'm sure for a given storm, it's worse or better, but there's a general understanding of what's going on. There's also preconditioning from below, and that relates to this variability thing I mentioned. But there's other questions about what drives storm-to-storm variability. So we certainly can't stop here and say, we understand the average response, that we're done. The science it has to advance past that point. So I wanted to sort of define ionospheric weather. I'm just going to extend that theme that Mendillo and Klobuchar started, the idea of an average pattern and an instantaneous storm time response and an absolute difference and a fractional difference. So this graph is a graph of global ionospheric maps. It's not a data per se, it's not a direct measurement per se, but it's a data product, and it's based on global network of total electron content. It's been extensively validated, so we can have some idea of its accuracy. Roughly speaking, it's probably 2 or 3 tech units accurate over the US where there's a lot of receivers, and maybe more like 1 sigma 5 to 7 accurate over the oceans. TC units over the oceans, and typically the TC units of the ionosphere will be anywhere between 30 and 100, 150 at solar max vertical. And so this is the TC estimate during a storm. This happened to be the April 2011 high-speed stream, and we took a snapshot of the TC. This was the average quiet time behavior, and this is the absolute difference with respect to quiet time, and this is the fractional difference. So the fractional difference is difference divided by the quiet time. And both of these measures are actually very important. You learn some things by looking at the absolute difference and some things by looking at the fractional difference. The fractional difference blows up during this nighttime when the TC is very low, and you probably can't ascribe too much to that. On the other hand, during the daytime, and this you can see the daytime is here, this increase is something physical. I'm losing my juice here. This increase here is something physical happening during the daytime, and we might call that a positive phase of the storm. So let me go to the next slide. All right, so we can also do the same thing, fractional differences. I think this is fractional difference with the models. And so we can compare the fractional difference with the measurement. with the fractional difference with the models. And the models, of course, is what's giving us the forecast. So we would step the models forward in time from the quiet time behavior, look at the fractional differences driven by some solar wind input, and get a sense of what the ionosphere is going to be doing. And you can see in this case, there actually is, at the same time as I showed you a positive phase, there is a positive phase right here in this fractional sense. So the model would have predicted that in this case. So that's still a little bit of work to do. So what we decided to do is we decided to break up the Earth into a set of grids, sort of large boxes. And although we can probably get data at a much higher resolution than these boxes, again, to reduce complexity, we're just making things coarser. And we want to see what the storm does in the different grid boxes. And so we divided it up. That's actually a misprint. It's 15 by 30, but so the basic idea is we want to capture regional positive and negative TEC changes relative to quiet time. And we're going to look at the statistical significance of those changes based on the quiet time variability. So in each one of those grid boxes, there's some sort of quiet time variability. It tends to be larger at the low latitudes and somewhat smaller at the mid latitudes. But the storm time response is going to be referenced relative to that. We're going to define a threshold level that says if you're above this level, you have a storm effect. And we're going to take duration into account. And we're going to compare the global TC map data to GITM output. Now, GITM is the model that we've done most of our work with. I'll show you some TIE GCM output as well. GITM is the global ionosphere thermosphere model that was developed at Michigan, and many people are familiar with it. It's a coupled thermosphere ionosphere model. And it's very interesting to do the coupled model. You could say that doing the coupled model is too hard a problem, but it's more interesting physically to do the coupled model because during a storm, both the thermosphere and the ionosphere undergo large changes. And so why not try to understand the coupled changes? And so I'm going to show you some metrics that are based on these calculations here. And the basic idea of the metric that we defined is the TC for a given UT lon lat instantaneously during the storm minus the quiet time divided by not the, I don't know if I...
Try this one.
Okay, thanks.
More conventional.
Okay. Okay, that battery's okay for now until I run it out. Not divided actually by the TC itself, but by the variability. So this metric basically says how many sigmas is the difference relative to quiet time variability. We found this was a much more robust metric than just dividing by the quiet time value because the variability associated with that is very important. And so we defined a metric for GIM. This is the TEC metric that is, again, this difference divided by the variability. We did the same thing for the model, but we had to add some caveats. We take the model TEC minus the model quiet time. We divide by not the model variability, but the actual variability. The reason is the model is way too quiet. The variability of the model during quiet time is way too low, and it tends to way over predict what the storm will do. So we change that, and then we scale it. We scale it because the model really only covers 100 to 600 kilometers altitude, whereas the measurements cover all the way up through the entire ionosphere over 1,000 kilometers. So we had to put some scale factor in there. The scale factor is determined by quiet time, and that's not perfect because when the storm hits, altitude distributions change and the scale could change. How much is below 600 could change, but this is just a first cut. So we wanted to do this, and we wanted to just sort of evaluate the model forecast driven by either a solar wind prediction or a solar wind data. And so I would say some success with this could be seen in this graph. So this graph shows you the time behavior of this metric for different grids. This happens to be the 30 east to 60 east grid cell, covering a range of latitudes. And the nice thing about it is you can see that before the storm hits, the metric is really hovering around zero. So it's really pretty good at telling us things are quiet and not being too erratic. However, when the storm hits, there's both the GITM, in this case, the observed is blue, in other ones the observed is black. But The observed is blue and the modeled is black, and you can see that both of them get somewhat perturbed. They don't work in lockstep by any means, but you could certainly see that the storm time behavior is different from the quiet time behavior. So then we set out to basically analyze.
Why is the south so much better?
South so much better? We don't have that figured out yet. We've probably tried to figure it out and couldn't quite figure it out. We've spent a lot of time on individual boxes here, trying to understand different aspects of the production and loss mechanisms, and it was exceedingly difficult to actually come up with a definitive reason why this grid cell was worse or better than this grid cell. And I'm not going to say too much about that, but it's just a very complex problem. Because basically the ionosphere is so strongly driven by thermospheric conditions, and it's all globally coupled. It can be very difficult to unravel. I want to add another element to this, which again speaks more to the phases. If you have, for example, these graphs versus time of the storm, you can see that although the magnitudes aren't exactly right, the model, which in this case is red, and the observation in black, often overlap in terms of these particular grid boxes and when there was a positive phase or a negative phase. So negative phase is down. These are all negative phases. So trying to inch closer to this. And then when we sort of did a summary of all of this, we came up with a graph like this, which I was absolutely thrilled at this graph. Turns out I was overly thrilled, but what this graph is telling us is the success rate of the model. And so it's the number of times the model matched the TC disturbances. So a perfect model would be 1, a success rate of 100% or 1, meaning every time there was one of these positive or negative phases in the data, the model was able to match it. And every time, and there wasn't any misses, any false alarms or anything like that. And we gave it a sort of a 3-hour coincidence window. So the model had to be within about 3 hours of the increase in the data, the matching, and we call that a success. So I thought that was a huge success rate, actually, given what I expected to see. When we drove the models with actual Omni data, we got a 40% success rate. I thought that was tremendous. We also drove the model with different solar wind drivers, different solar wind simulations that in a sort of pure sense could be eventually forecast, and they did worse, actually not very good in my opinion, but that's to be expected. We're at a very early stage of solar wind forecasting, and just getting the 40% with the data was I thought was huge. And yeah.
Just in case, could you explain what Omni is?
Oh, Omni, yeah. Omni is data. It's a data set that's hosted by NASA at the CDAW. No, it's called the Omni. Yeah, but it's a data set. Yeah, it's upstream solar wind data. Yeah. So it's data acquired at L1, which we assume is essentially the same as what the Earth sees. Solar wind velocity, solar wind magnetic field, solar wind pressure, and other quantities like that. And those are going to be the drivers of these models.
Back in the SISM days, similar comparison was done, not for GC, and it seemed almost hopeless to use Enlil, core held, etc. compared to Omni because it does so poorly at predicting the INFBZ in particular.
Yes. In fact, now one thing I should preface this is saying these are all high-speed stream periods. And so the BZ component is almost like a random variable. It's not, well, I shouldn't say that. It does go southward, not very large southward. The drivers for these storms is southward magnetic field, so you get reconnection oppositely directed to the Earth's magnetic field, and you let the energy in that way. These high-speed streams have very rapidly fluctuating magnetic fields, and so I'm not saying the models are better at that, but it's less of a shock to the system. These storms are more dependent on the velocity and the density of the solar wind than the magnetic field. These kind of storms, but you're making a very good point, which is that these simulations can be lacking in key details. And progress has been made on that, by the way. And I don't have the time probably to go through that, but So our preliminary conclusions from the metrics was the forecasts are more accurate than driven by solar wind models. And actually hitting 40% I thought was quite amazing. So even though it's real data, there's so many complexities in the system, hitting 40% I thought was quite something. However, it turns out if you look at my metric, there's a flaw in the metric in that I'm not counting for times when the model saw something and it didn't show up in the data. I'm only looking at the data and did the model match it. So the whole question of false alarms is sort of raising these averages more than they should be. And I'll show you an interesting case that we came across where that became a very interesting problem. And this is, by the way, the false alarm issue is why we don't use the model quiet time. If you use the model quiet time to form your percent increase, it gets way too large. But it's still a lot to evaluate. If you look at some of the metrics that the weather people use, they use these global metrics. Literally, the average altitude of the 500 hectopascal pressure level, average globally, is a metric they use to evaluate their forecast, meaning they forecast that altitude maybe 3 days in advance. Then when the 3 days comes around, they look at their model with the current data and they compare the forecast and they evaluate that in terms of what they call the anomaly or the error in that. That's one number for the entire globe. We're trying to do many numbers for the globe. So it's still very complex, and you'll have certain regions which do better than others. Certainly certain local times will be very different than others. Okay. So I just wanted to, so we started to plot things in this way. What this is essentially a scatter plot of all the positive phases that we might have seen in the model and in the observations. And so this is, for example, for the Halloween storm, and you can see that there are some occasional very, very